Hello everyone. In this video, I'm going to demonstrate how to use V-Grade 5S series software for physical vapor deposition or PVD processes. First, I would like to mention that V-Grade 5S software is made for engineers in two functions. The first kind are those who strive daily to maintain quality and yield of thin film materials. The second kind are those who design and configure thin film deposition equipment. For all the tasks involved, the modeling software provides critical validations and predictions on whether certain approach will allow you to meet manufacturing specifications, the kind of knowledge you would normally only acquire through years of experience and very tedious and tiresome trials. When you launch the program, you can see that there are several subpanels. In each subpanel, you can enter very detailed information how your deposition system is configured. Like most professional software, V-Grade 5S is packed with a broad range of functions. A typical user will only need to learn a few of those functions to carry out their job. That being said, V-Grade 5S is very versatile. It can model virtually any PVD processes one might encounter, including evaporated thin films, sputter-deposition, ion beam sputtered thin films, substrate motions of all kinds, 1-axis, 2-axis, 3-axis, linear motions, and so on. Your sputtering sources can be of any geometry, planar, cylindrical, hollow cathode, etc. The software also predicts how erosion of a target will affect thickness distribution. You can even model some absolutely unique, one-of-a-kind thin film deposition processes. In this video, I'm going to demonstrate one example, that is, how to design correction masks for a sputter deposition system. As we all know that a magnetron target in its lifetime experiences changes that cause thickness distribution to change over time. When you have very stringent uniformity requirements, one correction mask may not be adequate. You may have to use 2 or 3 or even more masks in order to maintain stringent uniformity requirements. I would like to mention that there are other techniques for maintaining thickness uniformity when the target becomes eroded through use. For the time being, let's start with the common technique of employing correction masks. Here, I'm going to open one setup or one experiment. In the geometry panel, you see information how your source, fixture, and rotation axes are positioned to one another, such as distance d, which is the distance between the rotation axis and the origin of the source coordinate system. Obviously, you can change the distance by typing in a different value. Now press the View 3D Chamber button. You will see a three-dimensional representation of your system. You can change your viewing direction. You can zoom in and out. Now if you press Move button, the fixture begins to move in the manner that you have specified. This 3D view provides a visualization for you to verify if everything is in the right places. If you have correction masks, once you enter them in the software, they will also appear here. Let me now go to the correction mask panel and add one mask. Now we have the mask in the chamber. You can change the shape and the position of the mask any way you want it. We will come back to this. I will now go to the source panel. In source panel, you specify the vapor source you are using. You need to define their physical shapes and dimensions, as well as how vapor plume is emitted from your source. Right now, a planar magnetron source with a circular erosion track is shown. You can certainly change to another kind of source. For example, you may have a magnetron source with an elongated erosion track. You can specify it here and then spawn. Now we have a new source that you just defined. If you have an evaporation source, which can usually be represented by a single point, you can enter the number 1 here and spawn. Here you have it. Let us now take a look how to specify the plume function. A plume function tells how vapor flux density from a source point varies with angles measured from a symmetry axis, which is usually the surface normal. Here, shown on the screen, is a typical plume function from a sputtering source. When I change the source to an evaporation source, I did not touch the plume function. A typical evaporation source can be described with a single cosine term with an exponent around 1.5 or so. Let's put 1.8 and eliminate the second term. Now this slightly focused plume is what you typically observe from an evaporation source. We have changed a few things. Let us revert to the original state by reopening the example. Right now, there's no correction mask in place. If we hit Run button, the program will compute. Here's the result. This plot shows the thickness distribution along a radius of your fixture. The thickness uniformity, or rather non-uniformity, is about 2%, which is not too bad. I want to point out a couple of things here. First, the values of the y-axis are not arbitrary. They are absolute thickness values in unit of nanometers per gram of source material consumed. You do need to enter the correct density of the material in order for these values to be correct. In this case, silicon is assumed. For each gram of silicon sputtered from the target, you get approximately a 3000 nanometer thick coating on your fixture, where you place your substrates. You may wonder how good your system is in capturing the material vapor. You can actually determine that by checking the material collection box. Run the program again. Now you see in material collection window a value 0.229, which means approximately 23% of the material vapor is collected by the fixture. The rest of the vapor gets deposited on other surfaces of the system. The 20-something% vapor collection in this kind of a system is in fact typical. Okay, that's a lot of a diversion. Now let us return to the discussion about correction masks. Here in the shadow mask panel, we have two masks. Let's check mask 1. It is now shown in the 3D view. It is a rather narrow mask, and it is offset from the source position. If you view the chamber from the top, you can see that the mask is placed at an angle from the magnetron. This is to prevent material deposited on the mask from falling on the target if it flakes off. You have two ways of modifying or optimizing a mask. One method is numerical trial and error. To do that, you go to the mask panel. Under the mask that you wanted to modify, press Edit Shape. In this pop-up panel, you can reshape the mask by changing these two columns of values. You can either use the arrows to change the values or type in the values you want. To make the mask symmetric in shape, you press Symmetric button. For the changes that you have made to take effect, you must press Keep button. Now in the chamber view, you can see the new shape of the mask. Another way of optimizing a mask in VGray 5S is to let the Mask Optimizer function to do that for you automatically. To show how it is done, I'm going to open a different experiment. This process has a planetary rotation fixture and an evaporation source. In the 3D chamber view, you can see how the fixture moves. A mask is installed. Let us first remove the mask. Compute. We get a thickness uniformity around 2%. Now put the mask back in and compute. We have improved uniformity to approximately 0.9%, which is far from the best you can achieve. Instead of reshaping the mask manually, we are going to use the Mask Optimization function. In the Mask Optimizer panel, you first load your input mask, which is the mask to be optimized. Next, you provide some constraints on the reshaping. There may be several reasons why you need constraints, one of which is the need of an installation provision or a handle for mounting. Without it, the result of optimization may be a shape that narrows to a point at both ends. Such a shape will leave us with no way of mounting it in the chamber. To prevent that, we can enter a minimal width to one end of the mask. When you try to achieve high thickness uniformity, all these details must be considered and taken care of. We don't need to pay much attention to the maximum width here. I will just load the input mask and allow it to be broadened by 1 centimeter everywhere. There are a few other parameters you can select to determine how the optimization should be carried out. We can take the defaults here, except that we change the number of iterations to 1. You also need to tell the program which mask to optimize. Mask 1 is to be optimized here. Now we are ready to hit Optimize button. It will take a little more than a minute to complete the optimization. The algorithm is searching for a mask shape that reduces the cost function. Still working. If you have forgotten something and wanted to stop the optimization, you can hit the Abort button. Okay, now we have an improved mask here. Compare the two cost function values here. The ending cost function value is much smaller than the initial cost function, indicates that the algorithm has successfully found a revision that yields better results. At this point, we can save the optimized mask. Let us call it OPTI1. Right now, the mask in the system is still the original one. Let's recompute to have a baseline. The uniformity is 0.89%, which we saw earlier. Now let us load the mask that we have optimized, OPTI1, which we just saved. Recalculate. The non-uniformity is reduced to approximately 0.4%. You can run the optimization routine repeatedly and try different cost functions and parameters. You should be able to find a mask that yields a uniformity that is much better than 0.4%. To see how effective this algorithm is in optimizing masks, we reopen the sputter-deposition experiment. This model has two masks. Both have been optimized through the mask optimization function in conjunction with numerical trial and error. The reason I did not use this process to demonstrate the mask optimization routine is because it takes several minutes to complete the computation when a sputtering source is involved. That is too long for this video. Let's first check the thickness uniformity without mask. We have a uniformity of 2%. Now we install mask 1 in the chamber and recompute. The result is very good. The uniformity is 0.06%. To actually hit this uniformity, you must have a very stable process. In some well-controlled sputter deposition tools, uniformities around 0.1% are actually achievable. This brings up an important subject: how stable a deposition process can be. It has a lot to do with the properties of the material, the components you are using, and how they are put together. One change that will always be present is the target erosion. This model, as opened, assumes that the prune function has this distribution. It is usually associated with a new target that has a smooth surface. You need two cosine terms to specify it. As the target surface becomes eroded, its prune function will be more cosine-like. We can easily find out what consequences it may cause. Here we eliminate the second term. Now this new prune is a pure cosine distribution, which represents a severely eroded target. Hit run again. The uniformity now becomes 1.9%. In order to achieve good thickness uniformity with this eroded target, we need a different mask. In the mask panel, we turn off mask 1 and turn on mask 2, which is significantly broader. Recompute. We again have thickness non-uniformity below 0.1%. Probably no one is surprised by this. In general, different materials have different vapor prune functions. Same material can have significantly different prunes at different stages of erosion. You may ask, how do I know what prune functions my target produces? In vGrade 5 Plus program, there is a fit prune routine. This routine allows you to determine unknown vapor prunes through least square fitting of experimentally measured thickness distributions. This will be the topic of our next segment. Stay tuned. Thanks for watching.